Hello and welcome to our final presentation. We are the Three Musketeers. My name is Sean Santoro and my partners are Mackenzie Rideout and Khalil Dahala. In this presentation, I will be discussing the problem definition, our design development, our design evaluation, our design results, and the final takeaway. Let's begin our problem definition by observing the track. The track is first broken up into 4 quadrants, 1 quadrant per team. Inside of those quadrants is a red dashed line. That is the starting zone for each team's device. Each team may also want to consider the dimensions of the track, as each of the 4 teams will be using the same real estate, the same amount of space, in order to win the maximum amount of points. And thus, it is vital to their design and the success of their design to keep in mind the dimensions of this track. The overarching goal of this competition is to maximize the amount of points that our device receives for completing certain tasks. Those tasks are shown in this chart. Each task is assigned a point value, and the goal of our machine is to maximize those point values while competing against other devices trying to accomplish the same goal. Because the overall goal of our design is to maximize the amount of points our design receives in the competition, we must keep in mind throughout the development of the design which tasks earn us the most points, so we can make sure that we are spending the most time perfecting the tasks that will help us receive the most points and be successful in the competition. To further understand the task at hand, we have a house of quality. The house of quality is great for a couple reasons. First and foremost, it allows us to see what the customer requirements are. In this case, those are the tasks at hand that our device must complete to be successful. And it also shows the engineering requirements in which we as a team need to consider and keep in mind while designing our preliminary and final design in order to ensure that we meet the customer requirements and our device is then successful. We as a team found that the 3 most important engineering requirements to ensure the success of our design was the operation time, the repeatability, and the adherence to the competition rules. If we kept these 3 in mind while designing our device, we were sure to meet the majority of the customer requirements successfully and thus end up with a successful device. Let's now discuss our function tree. Our function tree begins with our major function. Our major function is to maximize the design competition points that our device receives. This function can then be broken down into subfunctions. These subfunctions will include some of the things that we needed to do to ensure that our design was successful. These things include elevating a golf ball 3 inches in the air, gathering ping pong balls, and operating autonomously. Some of these subfunctions can be broken down even further into assignable tasks that our group members can work on to ensure the success of those subfunctions, which ultimately helps us realize our major function of maximizing our design competition points. Now let's move on to our morphological chart. The morphological chart is extremely useful and a great tool because it takes the subfunctions from our function tree and depicts certain mechanisms that can be used in our final design to complete each of the tasks and each of the subfunctions required in order to come up with a successful design. Now let's move on to our preliminary designs. Our first preliminary design includes things from the morphological chart, such as foldable arms to knock out the chew toys, a rotating arm to launch the torpedoes into the rotating center, and a lever arm to raise the golf ball 3 inches into the air plus. We also have pneumatic actuators and a pneumatic tank in order to assist in some of these functions, to make them quicker, more reliable, and better when we're competing against other teams. Our second preliminary design uses things from the morphological chart, such as scissor arms to push up the chew toys, a foldable ramp in order to launch the torpedoes into the rotating center, a telescoping arm with weights attached to it in order to raise the golf ball 3 inches in the air, and motors from our mechatronics kit in order to assist in these functions. Our third preliminary design includes things from morphological chart, including a wheel and foldable arms in order to knock out the chew toys, a scissor lift and weights in order to raise the golf ball 3 inches in the air, and a foldable PVC pipe in order to extend and reach the rotating center in order to deposit the ping pong balls. In this case, we are using a motor in order to assist our design to complete the functions and subfunctions at hand. Our fourth preliminary design includes scissor arms which push out the chew toys, a telescoping arm with weights in order to raise the golf ball 3 inches in the air, and the biggest difference here is a shooting mechanism which launches torpedoes or ping pong balls into the rotating center by means of a pneumatic tank and actuators to project the ping pong balls. Now let's move on to the evaluation matrix. In our matrix, you can see our 4 preliminary devices. Each of these devices are ranked against one another and how they successfully complete and meet the criteria necessary to be a successful device when we're competing against other teams on the track. It turns out that our preliminary design number 1 met the most criteria the most successfully, and thus it'll end up being our final design choice. The preliminary design choice that we chose to be our final design choice was preliminary design number 1. This is because, based on the evaluation matrix, it met the most subfunctions completely and successfully, and thus we felt and know that it is our best chance at maximizing the amount of points that we will receive in our competition. Next, I would like to expand on some of the functions in our final design choice. The foldable arms, which are intended to reach outwards and extend, hitting the chew toys out of our zone, are supported by pneumatic actuators, which are there to assist in the speed in which the foldable arms collapse and reach the dog bones before the other teams are able to push the dog bones into our zone. Next, we have a rotating arm, which was measured exactly to reach the rotating center. The tube laying on top of the rotating arm is a gravity-fed tube in which ping pong balls can then roll down and drop into the rotating center, thus making that design successful. Next, we have a lever arm, which is a very simple device and very simple mechanism, which raises the golf ball 3 inches above the starting zone every time to ensure that we do earn those points without fail. When evaluating our final design's performance, we wanted to make something visual so that we understood exactly what we should expect when we run this on the track against other teams. Here's a chart that shows what the possible points are for each subfunction and what we expect to receive in terms of completing each of those subfunctions. You'll notice that we don't even attempt some of the subfunctions possible. That was specifically and intentionally done so that we could focus on making sure that the success rate of the other functions we try to complete were high enough that we never needed to worry about not receiving the full amount of expected total points for our design. Now to discuss the final results of the competition. Our team was correct in assuming that reliability and quality was better than quantity. As shown in heats 1, 2, and 3, we earned 52, 42, and 94 points respectively. We didn't even come close to the possible 160 something possible points, but because we designed our subfunctions to have a high success rate, we were able to advance to the next rounds, as we were earning some points, which is much better than no points. Reflecting on the final competition, we were knocked out in the semifinal round. We noticed that we had one failed triggering, which can be attributed to our fast pace and non-concentration on what was going on throughout the setup procedure. However, when our machine did manage to trigger, we noticed that the removal of the rubber obstacles and the depositing of ping pong balls into the rotating center was a very reliable design, and thus we attribute that to the success of our design in reaching the semifinal round. Finally, to discuss the takeaways from the final competition and our final design, we found that simplicity wins. When you're designing your mechanism to be very robust, reliable, repeatable, and simple, it ends up performing a lot better than a machine that reaches for the stars but does so in a sloppy manner. Lastly, we found that building subsystems each week with the overall design in mind was key to the success of our project. That means that we could focus on making the success of the next subsystem that much better because we already had subsystems in place that worked well. So we didn't need to allocate more time to refining our designs, and we could spend time making the one that we were working on that much more successful. That is all. Thank you so much.